Great. Yeah, thanks. Let me first make sure you can hear my voice and you see my screen well, right? And also you see my laser point.
I can see everything,
Great.
yes.
Okay. Great. Thanks for the great introduction, and thanks for the organizers and everyone coming for this talk. It's, as you can see, this is a really challenging topic, right? What I'm going to do today is report what we have observed in tungsten ditelluride, which actually is an accident. It's the accidental observation. We not plan to do this, of course, it's not crazy enough. Once we observe this, right, it's come as a complete surprise. I'll explain actually how we end up with doing this, right? Why you measure the insulating state. But this complete surprise is really, on one side, I really enjoy it. I have to read a lot of papers to understand what's going on, and I learned all the works, exciting works, right? At the same time, as you also has mentioned, this is my first work as my starting point as career. So are we going to challenge the entire history of quantum oscillations, right? So it's really a big worry, right? So if you consider all this, it will become I was thinking about as like 30% of exciting is already very exciting, and then 70% of worry, and then you're gonna have to think about all the possibilities, right? We really spent very heavily thinking about what's going on. Can we find extrinsic possibility to explain this phenomena in the past 1.5 years? I believe still up to today, I'm still the one who have worked the hardest to think about what's going on. Can we have extrinsic origins? And the fact that we have published, we choose to publish the results, and I'm going to give a talk today, meaning that I failed, right? I failed to challenge it, and I need help. I need the help from the community. And to this reason, I think I really appreciate what King Mac has done. It's really good, video if you watch it. And very excitingly, so quickly, the result has been reproduced, right? So it's very, that's a very good part. And he proposed a explanations, which actually we have think about this for a long time, which I'm going to go through the details today. I think this statement, which I heard from the WTe₂, right, which they are the insulators, they show quantum oscillations, still stand well. I'm going to explain that. This is actually part of the motivation for me is to put intrinsic in my title. I think about this. Should I do that? Yes, because I want to know the answer, right? I want you to help me. So I put on this. And then you also notice that I have the S, WTe₂ insulators, meaning that I'm going to, for the first time, announcing the findings of a new example of quantum oscillations in insulator in WTe₂ system. So this is a bonus. Right? Thank you for coming, and also for the organizer. So I'm going to actually talk about two examples, not just one. Hopefully, it will make the case of WTe₂ more interesting. Okay, before I start, I should thank all those amazing people, right? So it's a new lab in Princeton. We come 2 years ago. We start from kitchen. It's all these guys, my lab members, convert the kitchen into the lab and see all this phenomena. And amazingly, this amazing group of people, especially I would like to mention Pengjie Wang, who really led the observation that we talk about today. So Pengjie Wang and Guo Yu and Yan Yu was led on the observation of the Landau quantization, and Yan Yu Jia, Pengjie Wang, and in collaboration with Aliyah Stanley's group, we work on the second part of my talk, the Excitonic insulators, which is actually in collaboration with the theorem and Rebuttal. We have the excellent crystals provided by the best crystals by Leslie Shroop and Bob Cover, and that's the good crystal of WTe₂ was born in Princeton in I think 2014, right? And then we keep benefiting from their excellent crystals, and the boron nitrides are provided by these Japanese groups. We have also a lot of discussions with Wang An, Shivaji, and Sid. Okay, so let me start with this material. Briefly mentioned, it's really I think, exciting material. It's still rising, right? Rising wonderland. And the lattice structure you see here, the atoms in blue are tungsten, and in yellow they're telluride. We have a lot of experiments on this material in the recent years. This is a base diagram that I was working before I came to Princeton, before this the current work. We figured out that the material is actually a topological insulator. It has quantum Smith-Hall edge mode, and it became a superconductor when you slightly dope it, right? So we were sitting on these problems for a long time now. Suddenly we got these new observations, and it's really interesting because it's a material located at this position where topology, correlations, and strong spin-optical coupling are both all important. That's why this material is really exciting, I think. Of course, I told you that this is a topological insulator. You have edge mode. We were very excited by the edge mode a few years ago, but then we want to make progress to do more complicated devices, right? To do more things like twist bilayer, for example. But whatever you do this device, you always have a trouble because edge modes now always carry the current, right? So if you want to make progress, edge mode in some cases very exciting. In some cases, you want to avoid it. So we kind of have to make a device that try to study this material without the edge mode contributions. This is a device that we come up. And by the way, the monolayer device is really at the beginning the reference because we want to study something else. But then we don't know what's behaving in the monolayer, what to do, right? So we made this device, monolayer device, as a reference where the material WTe₂ is in red here in the plot. Is encapsulated by boron nitride to make it high quality. And then we make a context so that it will touch the bulk of the WTe₂ monolayer, but not the edge, right? How to do that? You just put a boron nitride, which is the insulating layer, on top of the electrodes, but edge the end of the electrodes. So you can kind of realize something like this, right? You have a source electrodes go to the middle, the other drain go to the middle, and then you will measure current only through the bulk. If you do that, you will confirm, right, the insulator. So the resistance changed by order of magnitude, right, 4 order of magnitude. If you either undope it, right, to the charging neutrality, near the charging neutrality, or put the temperature, both temperature effect and doping effect has 4 order magnitude effect on the resistance, right? And then this means that we do achieve a high quality device that can avoid edge mode. If you have edge mode, the resistance will be on the order of tens or 100 kilo ohms, and we have a strong insulator. Okay, so next slide I'm going to show you is you just locate the gate voltage at the top, right? And then you see this. You do nothing. Watch the magnetic field. The resistance start to oscillate. Right now, I guess you have seen this data, but when you first time seen it, what's going on, right? You got surprised, very surprised. I'm still surprised. And you do some FFT. On this data, you will have 1/b period, right? Everything looks like the standard metallic SDH oscillations. And LK formula that follows, you can convert the frequency. Can you do that, right? I don't know, right? But let's close your eye, forget about you have very huge resistance on the order of 100 mega ohm, right? But you just follow the standard procedure of SDH, you can get, for example, right density, maybe on the order of 10 to the 12. % in the square because the frequency is 50 Tesla, right? You warm up temperature, you cure, everything looks like SDH, except the resistance, right? And you can check the gate dependence. You can see the oscillations only appear strongly in the insulating regime, but disappeared if you go to the metallic regime. Well, in metallic regime, you originally should expect it, but obviously because here mobility is low, right? So you don't see it.
Just for clarification, there was a question, are the oscillations at the neutrality point?
Yes, the one, yeah. And then, right, it's looks like, right, it's a property of the insulator, okay? Now the question, of course, now you're all interested, how intrinsic it is, right? Okay, let me first, I told you, I really tried hard, and I failed. I'm going to demonstrate how I failed, right? And then you can help, okay? You can ask. You have edge mode, right? Well, it's very different from condo case, condo insulator case, because there's a surface state. A 2D surface state can give you oscillations. But here you have a 1D edge mode, so the edge mode counts, because maybe you have edge modes form a loop, but they can give you a period in B, but not in 1/B, right? So edge mode doesn't work. Maybe you can think about this metallic island, right, as impurity. We'll have a lot of discussions, right? Aluminum, whatever. But here, can you have metallic island? if you look at data, the oscillation amplitude is really huge, right? On top of the 120 ohms, you have 60 mega ohms of oscillations. So any resistance, you have to change the resistance by 60 mega ohms, right? Whatever it's oscillating is very strongly insulating. And if you, I have the quantization data the same, right? Even more, dramatic. There in the quantized data, the resistance changes from 100 mega ohms to 100 giga ohm. It's really the property of the insulating state. You cannot explain this by any kind of metallic island. Now, your material has used in your device has, WTe₂ monolayer, boron nitride, palladium, and graphite. Right. Now, you look at the graphite, right? That's your target. This has been my target for a long time. And then, thanks for the great talk from a video, right? From Kim and Mac, which is very good. Help us try to. We was thinking about this direction for a really, really long time. So, I'm going to talk about it. But before I talk about this, my answer maybe, if I talk to you, go read, because we think about our answer must be written in the paper, right? At least to some extent. Go read my paper, right? You're not satisfied. Because at this moment, I guess we are all interested in hearing about what possible trivial explanations. There's fundamental reason for that. I do that too, because you are going to challenge, the history of quantum oscillations. Why you have missed for so many decades, right? Are you going to challenge people not only in space, but also in time, right? If I don't solve this problem, meaning that we're gonna hear more and more, right? Or you can keep up, we can always come up new, scenarios. Somehow I have a video block my slides. You can see my slides well, right? Okay, good. So in order to really solve this problem, yeah, it's not, my slides frozen. So sorry, give me a minute. Oh, but you can still see my slides?
We can see your slides.
Okay. Let me put this up.
So I do see a little bit of it.
Right. So I guess I need, in order to really solve the problem, I need a time machine, right? Maybe I can turn on into the future. And I tell you, see, there's so many quantum oscillations in insulators. Now you trust me, right? I cannot do that, but I have a time machine that can bring me to the past. Okay. This is a paper published in 2014. It's a very famous paper. I guess most of you have read it. 90% of people in 2D materials, 90% of people in topology, right, and transport have read about this paper. Okay, this is a paper from Princeton groups, exactly same group of people without me. Okay, but it was published 7 years ago, has been cited by more than 1,000 times. Okay, in this paper, this is the key data. It's everywhere on the main text. Okay, you should read it afterwards. But this paper really tells you what, right? The key focus in this paper is why this MR, magnetic resistance, goes straight without stopping. Okay, keep going. You increase the B resistance, keep increasing by 5 orders of magnitude, right? The MY is 10 to the 7%, meaning that resistance increased by 5 orders of magnitude. What does that mean, right? Meaning you are turning biomagnetic field, turning the semi-metallic WTe₂ in an insulating state. And key focus, the entire focus of this paper and everybody else in the community, right, is to try to explain why this happens. That's because there's an equal number of electrons in the holes. But now you see the quantum oscillations, right? And you see the RT, resistance as a function of temperature. You apply a little bit, like 2 Tesla, resistance goes up already. 14 Tesla, you see clear that's insulating trend, right? And the strong oscillation, for example, keep going, right? So if you look at the red curve here, figure C, means that the resistance keep going very fast, right? Increased by 5 orders of magnitude, but the material still responds to magnetic field very well, right? They lose interest to respond to E field for producing current, but they're very interested in talk to a magnetic field for cyclone motion, for example. And then, right, at 60 Tesla, you can, the data for the RT here is only 14 Tesla. You can imagine, right? But the 60 Tesla, the upturn of the resistance when you lower temperature will be very high. Okay, you will get into a good insulator at 60 Tesla. The point is, if you apply higher magnetic field, resistance will be even higher, and oscillation will become stronger. Okay, but this very intriguing aspect has been missed, right, by the entire community for 7 years, and right, I missed it too. Right, I read it. This is a paper why I got interested in WTe₂. I read it many times. I have been working on this material, single material, for 6 years, and I never realized it until I was sitting on the monolayer problem after many months. Right, so I missed it. Why we miss it? I think well, right. But the point is, we missed it. Okay, and this is the realization of quantum oscillations in insulators, in WTe₂ insulator, in a very different experimental setting. Right, it's no graphite, and it's a bulk material. It's not measured by my group. It's still Princeton group, but okay, it's after 7 years. So I think we missed it because we have a bias against insulators. Right? Insulators do not deserve quantum oscillations. So why we care about it? We just missed it. Okay, now, I guess you want me to go through. I'm going to leave this page, but before that, I'm going to you go read the paper. Every single panel of the data in the main text of the paper. I'm not copying this from supplements or something, right? It's here. Okay, so you're gonna see that. Why you don't see it? And now this problem is not for me, it's for you. Right? Why don't you see it? If you look at this little small figure, I'm going to still walk you through one little figure. Okay? Every figure is telling you this. Okay, the WTe is crying to you. If you look at this little small figure, what's plotting is 1/b, right? Oscillation amplitude as function 1/b, meaning that from the right, you see my little point, right? And then you increase the magnetic fields, the material is semi-metal. Okay, so it's oscillating. The electrons and the holes in the material start to dance. Okay, and then when you apply more fields, the material becomes insulator. You see, right? There's a little damps, right? As amplitude becomes smaller, you actually hearing the electron, right? Talking about there's one electron talking to everybody. Now, right, we're going to get into insulating states. Stop dancing. But then there's kind of maybe the holes, right? Stand up. Why not? It's very deep, profound physical question. Why not? And a sudden, right, all the electrons find a holes, right? They form pair and start to dance. This is what when I read more data, something like this, try to make it it's kind of a story of love, right? Okay, I'm going to leave the slides. So now I think I identified this bias against insulators. So maybe here I can identify another one. So in Kim Fast's talk, which again I really appreciate, because this is the effort that we all also have done, right? I'm on the track too. It's very reasonable, okay, thinking about this problem. And now you have graphite, you have applied magnetic fields, the quantum oscillations in graphite, right? Metal should have it. Can WTe₂ see it, right? But actually you have another opposite, the same argument, or maybe you can propose different ideas, right? If you have quantum oscillation in WTe₂, graphite may see it, right? So you actually have options. One, which is graphite origin. Option two, WTe₂ origin. Now you see your data, right? So in order to remove bias, we know how to grade students' example, right? You cover the names, then you grade. I cover the name. Maybe you remember the which one is which, but now you start to pick which one is input, which one is output, right? Without knowing the name. I would say, right, if I have to guess, I don't need to guess, right? I'm just giving you, I'm not trying to say this data tells us what, I'm trying to say bias. So if you have quantum oscillations, in the inputs, I would then imagine this bottom curve is the input, right? Because if it's much better oscillations, and at low fields, the blue curve don't have oscillations, the red, the purple one has observation. Right. So I would likely choose, if I forget about all what I have learned, I may likely choose, right, bottom one as the input. Now the bottom one is WTe₂, right? So, okay, I don't think this tells us anything. It's just saying that we have to be careful when we evaluate our conclusions, because bias can change that. And this is a second slide from Kim Mac, which it's a gate dependent. Just tune the oscillations by changing the electric field, right? The top gate, bottom gate are both tuned, and then you tune the electric fields and try to see what's going on. You look at this map. Here the argument still, just the map tell you correlation, right? And that's it. So correlation itself, I was talking about, right? You have to think about it. And then, I'll briefly comment on it. I should move on. Is there any really good correlations, for example, right? If you look at this is really good correlations. There's two curves. But, what I see from this data, maybe they have better data, but what I see from this two data panel, the oscillations in the WTe₂, right, it has a slope. But the dominant oscillation in graphite gate, is kind of flat. It's very interesting why graphite is gate independent. And then, the central region for the WTe₂ oscillation is really the circles I have, right? Which means that, if you tune the gate, WTe₂ and the, graphite will get independent and WTe₂ actually dependent. So we kind of, the very good oscillation or correlations here, kind of maybe it's only at a single gate. Right? If you look at this area. Also, I really think there's a lot of interesting things to be discussed, before we can make a conclusion. Okay, so so why does gate independent oscillation? Also, this slope at the end still become gate independent. Kind of interesting, but I don't know. I don't want to comment on too much on this. But there are three remarks here, right? The first one, WTe₂ should be kept at fixed density. It's not very precise because if WTe₂ is the exciton, you apply electric field that can change electron holes at the same time. Let's keep the total density the same. Exciton density is not necessary. So, and the second remark is that, right, only top gates, in this case, right, when the WTe₂, you may have exciton density changing, right? The bottom gates is also changing the density. So the only top gates only here really, does not belong to here. So anyway, just, these are all data related to WTe₂ in KingFast talk. And there's another part of the talk is about is another system, not WTe₂. So I'm not going to defocus on my talk. I'm not to comment on that here in the slides. But if you ask me, I think I was very happy to make comments on the other material system. Okay, so that's all for the WTe₂ in the talk. And right, I think KingFast talk was very nice try, right, produce our results and provide a alternative, I think, about this. But I think the conclusion is we don't know, right? His talk do not prove it, it's graphite origin, nor deny it. Okay, I'm going to try it hard because I tried it already, right? I'm just redo it. Ask, can really graphite work? Okay. So this is a graphite, best graphite device, right? Because they have boron nitride, top, bottom, encapsulate, and then the red is the graphite oscillation. Okay, it's a high quality graphite at the same thickness, 6 nanometers around what we have. We have 4 to 10 nanometers. It's a very similar thickness, so you should expect the best graphite will produce oscillation like this. It's very messy. But in our device, it's not, of course, not best, right? Because our graphite is exposed. It's on the top, for example, and then as polymer, right? We transfer using PC, and we only watch it for 5 minutes because we want to do it as fast as possible to avoid the degrading of the WTe₂. So you see, there's a lot of dirt on top of the graphite. Okay, if you think graphite can produce quantum oscillations, it means that you put dirt on top of the graphite, and you can convert this red curve into the observation we have, like this. Okay? I think that's crazy. However, we can still think about, can we improve it? Graphite doesn't work, I think. Maybe graphene can, right? Graphene can have this kind of, interesting, single frequency dominates, very well defined, even down to very low B, right? Maybe it's graphene, right? Then let's just think about it. Can graphene work? Okay. Now, if you don't have graphene, right, we work on graphite. If you want graphene, you want to isolate the single layer graphene from the graphite, which is 5 nanometer thick. The single layer, isolate that. And somehow, there's a lot of somehow you have to involve. You have to assume this very bottom layer of graphene kind of decoupled from graphite. Right? It will behave independently in order to produce the beautiful oscillations. And they have to couple to the WTe₂ independently. Okay? Very strange, but hey, it's let's give a red flag. Say, I don't know why, but let's accept it. Okay, now you have to explain can you really produce the oscillations in WTe₂ based on, for example, screening, right? What's the mechanism? You really have a little bit modulation of the graphene, because you have graphite where you don't see it, it's kept at the metallic state, right? So your tuning of the screening is really come from the single layer of graphene at very low field already, right? Meaning that your WTe₂ has to be very sensitive to a little change, very small change of graphene, because the oscillation, you know, we see the oscillation, for example, in this device at 0.5 Tesla. Right? Means that, you know, the best graphene device, if you check it at this frequency, you have to, you know, graphene, the starting point of graphene oscillations depends on the doping, right? So if you check the doping with on the order of 10 to the 12, that's the frequency that we observe. It's about 0.3, 0.4 Tesla. Meaning that, you know, graphene just start oscillate, you immediately notice it. Very strange how your screening can be so strong, right? And this is even, you know, it contradicts with the experiment. If it's graphene, any gate tune, change of any gate voltage, well, because graphene is the bottom layer, right? But then the electrons, if you tune the gate, will see the graphene first. So meaning that this graphene layer will be very sensitive to the gate. I mean, very sensitive is really very sensitive, because now you want to think about the single layer graphene, right? And then we see very, you know, unchanged for this device, you know, it's very insensitive. Right? So change of the, you can argue maybe it's not top graphite, it's bottom single layer of graphene from bottom, right? But you know, this WTe, the insulator, top gate, bottom gate, talk to each other, right? No matter which gate you change, the density of both gates will change. And in the range that we tune here from, you know, about more than 2 volts, it will change 10 to 12, like that. The density here will change dramatically, but that is not. Okay. By now, I think I don't want to continue. There's more flags. I think it's time I'll move on to talk about, you know, interesting data, but I will still give you flags if I see it. I think, you know, there's too many flags in this situation.
You have 5 minutes.
5 minutes? Okay. Well, okay, I should move on. So, okay, the point here is that, you know, if you see a very high, you know, probability data device, then you should see quantum oscillations and then like quantum regime, right? We already see this. This is in the papers. I'm not going to emphasize more about that. I really want to say that, you know, the Landau level here, if you think the peak is a single Landau level, then that's an insulating Landau level, right? If you're a single Landau level, you should see a resistance on the order of E square of H, right? H over E square, but here it's not, still 100 mega ohm, okay? The dramatic, the qualitative change is also inconsistent graphing the graphite gates. Anyway, I'm going to move fast, but the real concern, not concern, real puzzle to me here is why the mobility is so high, meaning that the onset field for the quantum oscillation is so low. Okay, high mobility what is something that I really want to learn from the device, from this data, and this is not the best device that we have. We have, you know, improve thanks, you know, to last these great crystals. We have another device made by very high quality crystals, and then we can indeed improve the device quality for the charge carriers, meaning that you can see how sharp the peak is. And to do that, because I told you metallic state should see quantum oscillation, right? I want to see it. So you see here, this is the FFT of the quantum oscillations as one of gate. Right? If it's in a very high I3, very high quality device, you see both electron holes. Okay, and then the insulating state happens when, you know, here, right? You can see there's very clear correlations between metallic oscillations and insulating oscillations. There's another flag here. If you want to claim graphite scenario, you're gonna claim this metallic oscillations also come from graphite, which you're gonna challenge. You now have to choose: challenge quantum oscillation history or challenge the graphene device history, right? Anyway, so what I want to say here is you look more carefully in this data, you're actually gonna think about extons, right? Electron holes insulating, okay? And then in the second part of my talk, I'm going to go fast. Is really to independent experiment. I'm not going to use quantum oscillations to tell anything, right? And then I will do independent experiments that to demonstrate or to kind of exclude all the other possibilities that we know for WTe₂, because we already have learned, right, WTe₂ for several years, right? We work on this problem, but still what's the origin for the insulating gap for the monolayer is still unknown. But we know the options, right? Options on the tables are the semi-metal, which is not. Okay, we know it's the insulator. I showed you. and it may have a single particle gap, for example, or you have a dirty induced, disorder induced localized insulator, or you have an intrinsic excitonic insulator. Okay, so in this independent paper, we work together with our collaborators. We demonstrate that it's not the other options. For example, in this tunneling experiments, we actually perform 2 types of tunneling experiments. I'm going to go fast. The gap we observed is always pinned at the Fermi surface, which means it's not single particle gap. Okay, because any single particle gap will do this. Well, you tune the gate, you will watch the position of the gap. You will have a slope. It does not. So this is not consistent with any single particle gap. Okay. It should be excitonic, consistent with excitonic. And then we also do the transport. I told you we have different quality of device. You can compare that, right? What we find is that higher quality device, you have better insulating state. And that's inconsistent with the disorder Coulomb gap, because it suggests that if you have better device, you're getting stronger insulating. So the intrinsic case should be already have an insulating state. Okay. And we also observed a anomalous Hall behavior in the Hall effect at this is temperatures are a little bit higher, because a low temperature cannot do fault proof measurements. It's very resistive. But if you watch the trend, right, from high temperature to low temperature, the resistance are longitudinal resistance change dramatically, right? Increase the resistance like an insulator, but the Hall effect is not like that. The Hall effect still looks like semi-metal. It's very strange. Typically, the Hall effect should diverge like the green background curve here, but it's not. So we have Hall anomaly here, which is consistent with EI, because in EI, insulating, your state becomes insulating, but your Hall effect will be carried by both electron holes, right? So you can cancel. Okay. So I think what I heard from this 2 WTe₂ insulator case is that yes, there's intrinsic Landau quantization in WTe₂ insulators. Okay, I told you I've tried very hard to challenge it, but I failed. And right, I really invite you to help me on this. But I think in this case, we have already missed many things, right? We don't want to miss another decades. I really suggest for any explanations, we should aim at explain 100% of data, not just we don't want to miss it again. Okay, so not 10% or 50%. For any explanations, we should not allow red flags. We should really think about are these explanations consistent with 100% of data? Okay, that's what I understand. And in this talk, I separately talk about 2 contents. Unfortunately, that's the external insulator. I go too fast. But I hope we convinced you that in both cases of WTe₂ bulk under high field, I think that's excellent, because the fact of the B square, right, the magnitude resistance is so strong and never stop. That related to equal number of electron hole, then become insulated. Right? Very similar case in the WTe₂. Monolayer, because right, I demonstrate this exciton. Okay, I think exciton is the key to understand it, but there's options. Exciton can be bosons, then become condensate, right? In this case, you don't have Fermi surface, and how you can produce the number of quantizations. And you may also have neutral fermions, neutral excitons, but fermionic and have Fermi surface. I'm not going to go through it, but I think I'll briefly comment very quickly. Patrick will talk about the bosonic case, I guess. And then, there's an interesting scenario where fermionic excitons may happen, proposed by Charlie, Sodium, and Centil, where, if you have spin charge separations, right, the holes will become spinor and holon, and then you can form fermionic excitons. And the key here is, can we identify experimental evidence for the spin charge separation? I think that's is an experimental question. And then, right, there's really no theory for WTe₂ consider all the details. For example, right, the WTe has 2 electron 1 hole bands, and I really emphasized mobility. Why so low mobility is the key. I don't understand. I have to figure out. For any explanations, I think we have to ask high mobility of what? Okay, we have to make the mobility make sense. And it's my fault if I don't bring up this one, because if you look at the panelist, I think right, he provides a hidden glue for us, together today. I have to mention this. I have about 1 year overlap with him, but it's unfortunate that he still comes to the physics, but I don't have a serious conversation with him. I think, I hope, I wish I could find it earlier. I can tell him, but okay, this is a paper I was reading, and which, we know that, right? This paper gives rise to the field of quantum spin liquid. If you read this is called spin down, and at in the beginning, they call it pseudo Fermi surface. And then it's so hard to find it, right? Ghost Fermi surface in the literature later. But, in the last, they try to understand this for the superconductors. I was sitting on superconductivity for monolayer for also many years. This is why, I got resonance. Okay, and there's another paper here. I'm not going to through details. So why you have neutral Fermi surface? Can you have Landau levels, right? This paper modulates explain that, but at the same time, he cured it because I think the gauge field is not stable enough. But this paper has different opinions. I'm not going to talk about it, but as maybe a historical echo, right? Landau, when he proposed his original Landau quantization of metals, he also threw it away. Okay, let's see whether it will be interesting historical echo.
I think we have to wrap up.
Yeah.
Well, let's thank this speaker. So yes, there were a couple of questions, and I believe Len Glisman was the first person who asked during the talk. I kind of didn't allow him, but please ask.
Yeah, thanks. Apologies for asking earlier. So you mentioned that the low temperature behavior resistivity is insulating, and mentioned that it's activational apparently. So if you look at the magnetic oscillations and follow, say, a maximum of oscillations and minimum of oscillations, plot is a function of temperature.
Where, which part of you talk about?
The early part, earlier,
okay.
even earlier.
Like this?
Yeah, this one, yes. Yeah,
yes.
So if, there's this nice plot of R-os over R0, okay?
Yes.
And my question is that if you just look, say, separately at R-os and R0 as a function of temperature, and plot, say, three curves, okay? So R0 is a function of temperature, or better, logarithm of R0 is a function of temperature, logarithm of maximum of R-os and minimum of R-os of some particular oscillations, say at 0.135, here, for example, and minimum. Okay, so you have three curves.
Right.
Log R versus temperature. How do they look?
Yeah, this
parallel or they veer off. I mean,
this one, you see, here's R0 as function. This particular device, a very low temperature device dependent. But for this one, when it's getting to below 3 Kelvin, the change is small. The resistance itself, but other device change more stronger. I think it's at very low temperature. It's not following the Arrhenius very well. Maybe very dramatically deviate, and but number is very high. And then a different device, some other device, even the mini Kelvin is still going up. I have another device, for example, this one. This device dependent. The second device, those are in our paper. So we have this. The oscillation amplitude here at very low temperature is hard to tell, because we also measure the two-pole resistance and how reliable you can trust R0, because it's very insulating. It's hard to measure. But what's the question? Right?
But it looks like the rate. What you show is that the ratio is increasing when you lower the temperature, right? So the blue curve.
Yes, and right. we have the plots in the paper. At a very low temperature, might be some saturations, but for example, if you rise from 5 to 30 Tesla, right, the decreasing follows well for the LK formula, but the low temperature is not, and it's hard to tell because how reliably we can measure resistance. How, for example, we're also getting the quantum regime, right? So what that effect at very low temperature?
Okay, thank you.
Yeah. I know that Professor Chalin Kodak asked first, but I think we have only one question, and I think it should go to Professor Kim-Fai-Mak. I apologize.
Oh, thank you. I just want to make a quick comment only. So you said that the oscillations is gate independent. Actually for an insulator with a clean gap, the voltage you apply does not change the density of the graphite. It only moves the Fermi energy inside the clean gap. So that's one of the explanations why the oscillation
for the graphite oscillations, are you using this pattern?
Yes, I'm saying that it's still consistent with the graphite oscillation, because the graphite, if you have a clean gap insulator, you sweep the voltage inside the gap, it does not change the density in the graphite. It only changes the chemical potential of WTe₂ inside the gap. The graphite density will remain the same.
Well, but you have WTe the insulator, right? They can think WTe as the dielectric. They have just like boron nitride, they don't have WTe. They have bottom gate and graphite, two sides. The capacitance between the two gates. If you do this effect, you're actually tuning the density of the two gates together. Right?
Okay, then I have to understand a little bit better how you apply the gate voltages then.
Right. Yeah. Yeah. That's why I think we have to talk. Let's talk. Thanks. By the way, thank you. But we have to talk.
I apologize. I do have to move on, and I think it might be reasonable to ask on the chat window, and maybe something can answer them if they're simple answers. Thank you. Let's thank the speaker.